All right, so welcome back once again, and we continue our discussion on the adder circuits in digital logic. So, in the previous model, we talked about carry look ahead adder, where we saw its operation and understood a drawback that it has a delay problem. The speed of that adder circuit was low because the carry ripples from one state to another. So, for example, this is, let's say, one bit full adder circuit. This is another one bit full adder circuit, and so on and so forth. So, example, let's say the 4-bit adder example here. So, here goes the carry in, C in, and then it has the output of the adder circuit in the form of sum, the orange line, and its own carry out, which becomes a carry in to the next stage. Again, it has a sum output, orange line, and the carry output, sum and the carry output. And final carry out of this 4-bit stage comes out here. So that's carry ripple adder architecture as a 4-bit example. A naught, B naught are the single bits of the two different word size of 4-bit each. So A naught to A3 are 4 bits in a one word of 4-bit size. B naught, B1, B2, and B3 is another uh, data of 4-bit size. So for a full adder, a 1-bit adder circuit, you have A naught, B naught coming it as input. Then A1, B1, they are to the second stage, A2, B2 to the third, and A3, B3 to the fourth stage. And that's how this is a carry ripple adder where you have a simple architecture. It could be 4-bit, 8-bit, 16-bit, and it is efficient, less power, less area because less number of logic gates inside this architectural block. But the problem here, the carry generated from the previous stage goes to the next stage. That's how we call it a carry ripple. And the sum, the orange line, has to wait before the carry propagates from previous stage to the next stage, and that makes it slower architecture. So to counter this, there is another architecture or a block or a logic called as carry select adder, where you use two carry ripple adder circuits. So in the top portion, here is the example for a 4-bit adder, and the bottom is another carry ripple adder. So two carry ripple adders. So you see that A naught, B naught, they are inputs to the top stage, and also these lines coming down, becoming an input uh, to the bottom stage of carry ripple. Similarly, A1, B1, they are inputs to the top and the inputs to the bottom, A2, B2, and A3, B3. Now, you have the carry in to the top stage. We assume here that the carry in is logic 0 that is coming to the stage. And then this carry ripple adder circuit works as we just explained in the previous model, and also we recalled right now here the operation of this block. And then it has got C out as a final stage output. And the sum of each blocks are the orange lines. Similarly, for the bottom block, we assume the carry here, C in, the input carry coming to the circuit is 1, logic 1. So we are kind of We are assuming here carry to be 0 and assuming carry here to be 1. And again, the output of these full adders in the carry ripple bottom section are the sum, the brown lines, sum outputs, and its carry out is here. And look at this orange line, that is the sum outputs from the top blocks of the carry ripple. So now what we are seeing here, we are using multiplexers, 2 is to 1 multiplexers, where the two inputs to each of these multiplexers are the sum outputs of the top and the bottom carry ripple adders circuits. So brown is the sum output as from the bottom structure, and the orange line is coming from the top one. Similarly, brown and orange, here brown and orange. So 2 is to 1 marks circuits will select any one of these two lines. These are the sum outputs, individual bits of the A naught and B naught. Depends on the whether C in, that is the select line now here for all the mux, and here also the final mux will see whether the C in is logic 0 or logic 1. So the top architecture and the bottom architecture, they are carry ripple adders, 4-bit each. They will work as what we just saw. They will work as carry ripple adders, slow, and they will produce their sums, and they will also produce their carries. Okay, and assuming that C in here is 1 and C in here is 0. And then based on whether C in is 0 or C in is 1, the one of the sum output here gets selected as a final sum. So that is sum naught S1 based on the select line, whether the sum from the bottom or the sum from the top will be selected as a S1, then goes S2, then goes S3. And look at this now, the C in is also common select line to all these 2 is to 1 mux, and this is the final 2 is to 1 mux for the generating the final carry out of this complete architecture. So that is C naught. So the two inputs for this mux, which is 2 is to 1 mux, is the C outs from the top and the bottom carry ripple adders. Select line is C in is equal to 0 or 1. So whether it's C in is 0 or 1, this C out from the bottom or this C out from the top carry ripple adder will be connected as a final C out. Okay, so eventually what we see here, you have A naught, B naught up to A3, B3. Those are the inputs, 1 bit each to both top and bottom. You see that these lines are the inputs coming from the top. They are inputs 4 bit each to the top and bottom carry ripples, and based on the final sum S0, S1, S2, S3, that is 4-bit sum, and the final C out, that is the 5-bit word size, is available at the end of this addition. Whether the C in was 0 or 1, if it is 0, if it was 0, then this top block is uh, is actually working, and its sum output is here that gets selected and connected to the final sum here. Similarly, this orange line gets connected at the S1, this one, and also here S3. For this final C out, of course, this line gets connected as a C output. So that's how you get two word size of 4 bits each. You have the final 5 bits output. You append this carry as a MSB here to get you the final output. And if the carry was 1, let's say, so C is 1 here, then the bottom architecture of carry ripple adder gets selected. Its output gets selected in the form of these brown lines. They are the sum lines. They are then connected to the final sum lines here. Okay, and again, this Cin is equal to 1, which is a select line here. That means this C out line gets appear as a final C out. So the conclusion here can be drawn in the favor of a carry select order adder, that it although consumes more power due to extra hardware, it is efficient in reducing a delay as compared to the standalone carry ripple adder. So as we can see that when there is a carry is equal to 1, whether the initial carry before the start of a bitwise operation or the carry that could be generated intermediately between the stages, as we can see here, either upper row or the bottom row. So if there is no carry generation, whether it's initial or in between the stages, you can see that the sums from the top row, that is the orange lines, they are available. And because C in, let's say the initial carry is equal to 0, we have assumed that, then the orange lines, which are the sum outputs of the from the top row, gets connected to the final sum lines S0, S1, S2, S3. And similarly, because the initial carry C in is equal to 0, the C out uh, from top or bottom row would be selected based on if C in is equal to 0. So obviously the top row's C out gets connected to the final C out to be a final outputs for sum and the carry of this complete adder circuit. However, if there is C is equal to 1, for example, at the beginning, then the bottom row is activated and the brown sum lines are then enabled, or let's say the selected, because C is equal to 1, and these S0 to S3 lines receive the brown sums, the signal coming from the brown lines. And obviously A naught, B naught, A1, B1, A2, B2, A3, B3 are the parallel inputs to both the top rows and the bottom rows. You can see that they are coming like this. They are coming like this. So again, if the carry, okay, initial carry seen is equal to 0, but let's say intermediately uh, between the blocks, if a bitwise addition, let's say A to B2 is done and the carry gets generated right over here, then C in is equal to 1 here. But this is an initial carry is equal to 1. But you see that this is also the select line right over here. So if the initial carry is, I mean, the carry logic says that the carry has been generated intermediately. And that means the particular block from the bottom row uh, would be enabled to calculate the effective sum, that is the brown line. Of course, then it means the carry is rippling or from this stage, let's say, because at this stage the carry got generated. So carry gets propagated from this stage to the final stage, that is the MSB. So there is this delay right over here, and then accordingly the sum line, the brown, gets connected to the S3, for example, right over here. Similarly it could be but other stages, if the C has C intermediate carry has not been generated, so that it means your sum lines are already available. These brown, the orange lines are already available, and they are selected because seen now we understand that the carry did not generate internally. That means the sum lines receive the orange outputs. So there is no way or the question of carry propagation at these stages, intermediately, because there is no carry generated. So the conclusion here is this architecture is relatively faster as compared to standard carry ripple, where the carry ripples through all the stages. However, due to parallelism here, the top row and the bottom row, we have conquered and divided and conquered the structure, that if there is particular intermediate or in the beginning the carry it's generated, accordingly the select line of the multiplexer decides which multiplexers receives which block or which row to be connected to the outputs. Similarly, for the C out here, the final stage depends on if the carry generated, the this line gets connected, or if not, then this line gets connected. So the delay gets reduced. Carry in select adder, carry does not need to propagate through all the stages. Rather, it just propagates intermediately only when it gets generated, either at the beginning or at the stage. So hope you found this model useful. If you did so, share it with others for wider reach, and stay tuned for more engaging content like this. Till then, wish you happy learning. Let's say this is a 4-bit adder example. If there is like 8 bits to be added uh, for both the words A and B, each carrying 8 bits. So think of the structure. Let's say the bottom 4 bits are fed to the top row, and the top 4 bits fed to the bottom row. This could be the idea of logic generation. Okay, so that's all.